this lecture, I will explain speed control of DC series motor. The first method is flux control, and second is rheostatic control, and third one is applied voltage control. In this flux control, so I have a field diverter control, and the second one is armature diverter control, and third one is tapped field control, so tapped field control, and D is series parallel connection of field. So generally, if I am connecting an external resistance in series with the field winding for a particular value of load, the load current is same, that means load torque is same, constant. The load torque is constant. The current which is flowing through IA is constant. IA we can't change by adding an external resistance in series with the series field winding. Why? Because the load torque is constant. If IA is constant, the current which is flowing through series field winding is also constant. The flux which is developed is also constant. And there is no change in the current which is flowing through series field winding for a particular load. So that's why we can go for the field diverter control. The first method is field diverter control. I am connecting an external resistance in parallel with the series field winding, and this combination is given to supply voltage. The current drawn from the supply is line current. The current which is flowing through series field winding is series field winding current ISC, and the current which is flowing through external resistance RX is IX. If you apply KCL at this node, IL is equal to ISC plus IX. For a particular value of load, so I am calculating at a particular load, RX decreases, then the current which is flowing through IX is increases, and the current which is flowing through series field winding decreases, in order to maintain the load torque is constant. If ISC decreases, the flux is developed, or flux produced by the series field winding decreases. We have one relationship, N is directly proportional to EB by 5. If 5 decreases, the speed of the DC series motor is increases. As the load increases, yes, another load at load 2, again the IA2 value increases. Okay, the IA2 value, this is called the IA, the current which is flowing through armature. RX value still further decreases. Either you can decrease for the first load, nothing is a problem. RX is still further decreases, IX is further increases, ISC is further decreases, in order to maintain the IA is constant. In a series, IA is equal to IL. So here we are diverting the current which is flowing through field. Then the flux which is produced by series field winding decreases and the speed is further increases. The speed is further increases. If you draw the characteristics, speed versus armature current without Rx, this is a normal curve. Why? Because speed is inversely proportional to Ia under normal operating condition. So with Rx is included, so this is at Rx1, Rx1. This is Rx1 and Rx2. With this Rx1, the speed will be, the speed versus Ia characteristics are like this. With this Rx2, the characteristics is like this, and Rx2 is less than that of Rx1. So decreasing of Rx. Simply, if you apply current division rule, the current which is flowing through series field winding is equal to total current armature current into the opposite resistance Rx divided by Rx plus Re. If Rx is variable, the current which is flowing through series field winding is also variable, and flux which is produced by the series field winding is also variable, and the speed is also varying. And in overall observation, if you observe, the current which is flowing through series field winding decreases, the speed will be increases. Then this method is suitable for above rated speeds. And coming to the second method, is armature diverter control. That is B. So now this is a series field winding. I am connecting an external resistance in parallel with the RA. So these are the two terminals, EA1 and EA2, and the armature resistance is RA, and series field winding resistance is RSC. So I am giving the supply voltage V. The current drawn from the supply is line current. The current which is flowing through armature is IA, and the current which is flowing through external resistance is Rx. So for a particular value of load torque is constant, yes or no? Constant for a particular load. If Rx increases, the current which is flowing through armature is decreases. If the load torque is constant, torque is directly proportional to flux into Ia, and phi 1, torque is directly proportional to flux into Ia. If Ia decreases, the flux which is produced by the series field winding increases. The change in S, this one is changes, then only the load torque is constant. Okay, so why I am representing torque is directly proportional to flux into Ia means the same current is not passes through series field winding and armature winding. That's why I am writing the generalized equation, torque is directly proportional to flux into Ia. Suppose if Rx decreases, Ia increases, and the flux will be decreases in order to maintain the load torque is constant. If a flux increases in this case, the speed is inversely proportional to 5. The speed is decreases. Flux decreases means speed will be increases. Okay, speed will be increases, but we are adding an external resistance, right? We are adding an external resistance. The Rx is added. The Rx value is further increases, and Ia will be further decreases, and the flux will be further increases, and the speed will be decreases. And this method I am explaining, this is in between these two. In between these two, if Rx increases and again Rx will be decreases, what will happen? But this method is suitable for below rated speeds. Below rated speeds. And the third method is tapped field control. So it's a very simple method. It is tapped filament control. So I am connecting a number of nuns are like this. Total section. Suppose the current which is drawn from this one is Ia. Okay, it has a equal number of turns. If the total is n, and that is divided into 4 section, n by 4, n by 4, n by 4, and n by 4. Okay, I am giving a supply voltage. So here I am providing a switch. So this is one, second position, third position, and fourth position. If the switch is at one position, total number of turns is n. N is called the total number of turns. So I think you may confuse, instead of representing n, I will use t. Okay, so n is assigned for speed, that is in DC motor. So total turns is t, and then flux is equal to mmf divided by reluctance. mmf is equal to number of turns into flux divided by reluctance. So, and if turns are increases, the magnetic field which is produced is increases. The speed is inversely proportional to flux, and the speed will be decreases. This is about the first case. In the first case, if you go for the case 2, that means switch is at position 2. The switch is at position 2. So this will be cut off. The switch is moved to like this. The total number of turns are included is t by 4 plus t by 4 plus t by 4. That should be equal to 3t divided by 4. Then the flux will be decreases. Why? Because number of turns are decreases, flux is decreases, and speed will be increases. And coming to the case 3, in a case 3, switch is at 3, only total number of turns are now included is t by 2. Again the flux decreases, the mmf decreases means flux decreases, speed is increases. Coming to the fourth, switch is at 4, only I have a t by 4 number of turns, the flux decreases and the speed is further increases. So by this method we can control the speed of a DC series motor. We can control the speed of a DC series motor. And after that, one more method is there. We discussed the field diverter control and armature diverter control and tapped field control. The third method is series and parallel. I think it is a force connection of field. So if you are connecting, so this is T by 2 and T by 2, and the total turns is T. The mmf is full, flux is directly proportional to yes total number of turns, and the speed will be less, and the flux is high, the speed will be less, and the same turns are connected in parallel one to another. This is T by 2 and T by 2. If these two are connected in parallel, so T by 2 is parallel with T by 2, then this is T by 4, then flux is directly proportional to T by 4. The flux will be 1 by 4th. The flux will be 1 by 4th. The speed is inversely proportional to flux. The speed is inversely proportional to flux. It is 5 by 4, means the speed will be 4 times. And this is about the field diverter control. Uh, the first method is field diverter control. This method is called the series parallel connection of field. Okay, so with multiple turns, so thank you, students.